Okay, this is question number 9 from the first of the revision quizzes, and it is a parallel system. It says a system consists of two subsystems, so not necessarily components, but it works the same way. A and B with independent failure times arranged in a parallel state as shown. It says A has a hazard rate 0.2, B has a hazard rate 0.3, and then it asks us to find the probability that the system survives until time t equals 1. And then the hazard rate of the system at time equals 0. So let's go onto a clean page and start working some of these things out. So the first thing we need to realize is that it's actually asking us to find the probability that it survives until time t equals 1. Well, that's the same thing as the reliability at time 1. So that's part 1 of this question. Equals what? So we need to find an expression for r of t, and for a parallel system, we're given that the equation for a reliability function is 1 minus the ugly product sign, r equals I to I equals 1 to n of 1 minus ri. And it looks like an ugly function, but this basically works the same way. And if you haven't seen these very often, they can look a bit scary, but that's just multiplying together this term for all the values of r that you've been given or that you need. In other words, multiply this with the reliability of each of the parallel terms, or each of the parallel components or subsystems, depending on what you're given. So in this case, well, what do we know about the reliability functions for each? Well, we were told that the hazard rate, the instantaneous hazard rate, was 0.2 and 0.3. And that means they have no relationship with time. They don't change over time, and that means they're exponential, as per the memoryless property of exponentials, which is that h of t or r of t or whatever it is you like to use to denominate it is constant. And we see that a lot, so hopefully you've got the hang of that already. So for this system, we know that both of our subsystems are exponential functions, and the r of t, the reliability function for an exponential function, is given by e to the minus lambda t. And we should have seen that a couple of times already. So our r of t for this parallel system is going to be equal to 1 minus, and now we're going to multiply together the reliability functions, 1 minus the reliability, can't say reliability, 1 minus the reliability function for each of the terms. So it's 1 minus e to the lambda a multiplied by 1 minus e to the minus lambda b, and this always turns out to be e to the minus lambda a plus e to the minus lambda b minus e to the negative lambda a plus lambda b. I forgot the t's, all multiplied by t in the exponent. So that is the reliability function for any set of parallel exponential components or subsystems. So what do we know about this? What do we know about this number, lambda? Well, when we're given the exponential, let's just come back. When we're given this 0.2, 0.3, that's telling us h of t is equal to 0.2, say, we'll take the first one, and h of t is also, if you recall, equal to little f of t over the reliability function. Now these are, if you look up these straight out of the table, go to number 44 and 45, you'll see that 44 is lambda e to the minus lambda t, and r of t is e to the minus lambda t. So you pretty quickly see that those two cancel out, and the lambda that we're given actually is, the hazard rate that we're given actually is lambda. So we can plug those straight in nice and conveniently. So this actually turns out to be equals e to the minus 0.2t plus e to the minus 0.3t minus e to the minus 0.5t. So that's our r of t for the system, and then so if we need r of 1, all we have to do is plug in 1s for all of the t's here, and we'll get e to the minus 2, we'll get e to the minus 0.2 plus e to the minus 0.3 minus e to the minus 0.5, and that's going to give us 0.953, or 0.95 to 2 decimal places. So, okay, that's part 1 done. Now, the part 2 said, what about if the, what did part 2 say? Let's check it out. It said, find the hazard rate of the system at time t equals 0. So, let's just, I'm going to go to a clean page here. So, what is the hazard rate now of the system? The hazard rate of the system. Well, we're given that's always equal to f of t over r of t, little f of t over r of t, and this is actually equal to minus the derivative of r of t over r of t. Now we've already worked out big R of t, and I'm just going to use the symbols because this turns out to be the same every single time for this parallel exponential subsystems. Lambda a t plus e to the minus lambda b t minus e to the minus lambda a plus lambda b t. So this is the general case. So for time equals 0, let's ignore that for a second. So this is r of t. What is this going to equal? So if t is 0, then this whole thing goes to 0. If t is 0, that goes to 0, and that goes to 0. Well, these all become 1. 1, 1, 1. So all we end up with is 1 plus 1 minus 1 is 1. So that was easy. What about little f of t? What does that equal now? Well, we're going to get, so we're taking derivatives of each of these terms. It doesn't really matter whether we're taking plus or minus at the moment, so I'm just going to forget about the minus sign and take it as the derivative of that term. So all we do is we're bringing the minus lambda a in front, e to the minus lambda a t, minus lambda b, e to the minus lambda b t, and then plus, we're going to get this whole thing, lambda a plus lambda b, e to the minus lambda a. Doesn't matter what that term is, it's multiplied by t. So the point here is that these t's are all going to be 0 as well in this case, because we're looking for the hazard rate at t equals 0. And when t goes to 0, that one goes out and becomes 1, that one goes and becomes 1, and that one goes and becomes 1. So this thing is equal to, well, now I'm going to take the minus, because that was the negative of what we're actually looking for to put into our formula up here. It's minus the derivative of t. So what we're actually going to get for little f of t is always going to be the negative of that, so lambda a plus lambda b minus that, which is lambda a plus lambda b, and that's always going to equal 0. So it doesn't matter what our lambdas are that are given. At time t, the reliability of parallel exponential subsystems is 100%. In other words, there's a 0 instantaneous hazard rate for that function, because the reliability at that time is always going to be 1, and that should tell you all you need to know, really. And the instantaneous failure rate, if you take the derivative of reliability, is always going to equal 0. So I hope that makes sense. Happy to take any other questions if it doesn't.